All right, guys, are there any questions on the homework assignments from the factoring 1 or factoring 2 homework? Yes.
Number 9.
Borrow it for a second. So we'll look at this one here first. Now, the first thing we want to look for is a greatest common factor, a number or variable that will go into all three. Now, this one here does have a greatest common factor of 3. So we divide each term by 3. 15n squared is going to become 5n squared. 9n minus 2. So that would be the first place to start, is with the greatest common factor. Now, from here, we'll have 2 sets of parentheses with 3 spaces. Since the third term is negative, our signs are going to be opposite. One's going to be positive, one is negative. Now the factors of 2 are going to be 1 and 2. N squared will have n and n, and then we'll have 5 and 1. Because luckily there's only one set of possible factors. We just need to make sure we have it set up correctly. Now 5n times negative 2 is negative 10n. 1 times n is plus n, which gives us a negative 9n that we wanted. So luckily for us, we did set it up the way we needed to first. Yes. Yes. Any other questions or any other ones we want to see?
Number 1.
Okay.
I cannot solve that one to save my life. But now I had to get a new one for the last one.
3p squared minus 2p minus 5. Now for this one here, there's not a greatest common factor between these 3 terms. So we'll start off with our 2 sets of parentheses with 3 spaces. Since the third term is negative, our signs are opposite. Now the factors of 3p squared, well, we'll have p and then we'll have 3 and 1. The factors of 5 are 1 and 5. And the most likely we're going to need to split them up. We don't want 3 and 5 multiplying together, so we'll have to put them next to each other. And then we'll distribute this out. 3p times negative 1 is negative 3p. 5 times p is plus 5p, which gives us a positive 2p, which is not what we want. So, well, it is, but it isn't, because we don't want. So we need to switch the signs, and this time we would have positive 3p minus 5p, which is negative 2p that we wanted. So that would be the correct answer. 3p minus 5 times p plus 1. Yeah. If we have the correct number but wrong sign, we want to flip the signs. Any other questions on this here? Now, these here that we're looking at today are going to be considered, or mainly I'm going to classify and most classify them as special factors. They factor in a special way.
Are these the ones that are like, the ones that we could put them into one and then just put like square root?
Yeah, so these first few are indeed that. They would be considered perfect square trinomials. Now, there is a set way that we could technically factor them, because it's following our a squared minus 2ab plus b squared is going to be a minus b squared, or we'll have a squared plus 2ab plus b squared is equal to a plus b squared. Is the definition for it. I wouldn't write that down, mainly because us going through factoring it the way we normally would, the way we did the first 2 for the homework questions, is going to be just as fast as using that there. Because it does take us a little bit longer to work through it, but when y'all are doing it on your own, it's sometimes a little bit faster. Now, first thing we look for is greatest common factor. Well, there's not a number that will go into 4, 4, and 1 besides 1, and that really doesn't help us. So we'll have our 2 sets of parentheses with 3 spaces. Since the third term is positive, our signs are the same and they match the sign of the middle term, which will be negative and negative. Now, normally we start off with the first term, factors of the first term, and then move on to the third term. But here the third term is, and the only factors of 1 are 1 and 1. Because if the third term has some nice factors that are easy, I'll do it first. Doesn't really matter. Now, for first term, 4x squared, well, we'll have x and x. Now, the factors of 4 are 1 and 4, or so it's 2 and 2. And if we check this here, 2x times negative 1 is negative 2x. Negative 1 times 2x is negative 2x, which does indeed give us, so that is the middle term we wanted. And again, the reason this is special one is because one of our factors is 2x minus 1, and the other is indeed 2x minus 1. So we could say, or this is written as 2x minus 1 squared. Either one of these is the correct answer. You just need to pick one. We can rewrite it as 1 set of parentheses squared, or we can have it as 2. Questions on this here? Are we ready for the next one? 16b squared minus 40b plus 25. For 16b squared, yes. 40b, yes. Is 4 a factor of 25? No. So unfortunately, there is not a greatest common factor, but it is still good to look for, because it's good to start off looking for that there. So since the third term is positive, our signs are the same and they match the sign of the middle term. Now, not all of these are going to be minus and minus. There are some that will be plus. It just works out that the first two are minus. Now we look at the factors of the first and third. Well, in this case, unlike the first one, we don't have a nice one. We're 1 and 1. But we do know that we will have b and b. If the variable had been with the 25, it would have gone in the third spot on both of those. Now the factors of 16. 1 and 16, 2 and 8, 4 and 4. I have a feeling we know which one we want. 4 and 4. 25. 1 and 25, or 5 and 5. 5 and 5. Yes. Squared. I'm just saying or, so you could have it as 4b minus 5 times 4b minus 5. That is the correct answer. Or you can write it as 4b minus 5 squared. You just need one or the other. Questions on this here? We'll go on to the next one. And if y'all wanted the answer to this one here, it is 10x plus 9 times 10x plus 9, or 10x plus 9 squared. Just if you wanted that answer. Now these here, I think, are one of the types of factoring that we covered, especially with the special type, that y'all liked more than the rest. Is this here is the difference of perfect squares. And the theorem is that a squared minus b squared is equal to a plus b times a minus b. If we have two terms being subtracted and both of them are perfect squares, we can rewrite it as something times themselves. Then it's the difference of perfect squares. So if we look at these two here, is n squared a perfect square? Yeah, because it's the same as n times n. Now I'm going to rewrite it with parentheses, n squared, so that we can see it. Because the main reason I do that is if I don't, and we're saying, okay, it's n times itself, so n squared, it looks like I just rewrote the same thing over. So putting the parentheses kind of helps us see it is n times itself. We don't necessarily have to do it with 25, because what times itself is 25? 5. That's a little bit easier to see that it is 5 times itself instead of just rewriting n squared. So a in our case is n. B in our case is 5. So this is n plus 5 times n minus 5. And that's it. Because I think these are some of the ones that y'all enjoyed more than the rest. Because as long as it's perfect squares, it works out. Now for some of them, it could be that it is a difference of perfect squares. There's just a greatest common factor we have to pull out. So we'll pull that out and then go from there. (16n squared minus 9). Well, 9 we know is a perfect square, 3 and 3. How about 16n squared? So 4n, and 9 is 3. So we'll have a, which is our 4n, plus b, so plus 3, times 4n minus 3. And that's it. Now if you find rewriting it as 4n squared minus 3 squared being helpful to be able to factor it out, do that. If you don't, you don't have to. Questions on this here? So you feel comfortable with these? Yes? Let's look at this next one here. A to the 4th minus 9. Is 9 a perfect square? Is a to the 4th a perfect square? It is. Because what times itself would be a to the 4th? A squared squared. Because powers of powers multiply. Or a squared times a squared would be a to the 4th. So we can still do the exact same thing. It's just this time our a terms, our first set of terms is going to be a squared. So we'd have a squared minus, or well, plus 3 times a squared minus 3. Questions on this here? Now a squared plus 3 is fine, but the other one I have a squared minus 3, yes? That's kind of the same thing as what we factored, difference of perfect squares. Because a squared is a perfect square. Is 3 a perfect square? No. So that's as far as it goes. Because whenever we have a power greater than 1 attached to a variable inside these parentheses, we do need to check to see, will it factor? Can we reduce it? But this is as far as it goes. Questions on this here? K to the 4th minus 36. Yes. So we can rewrite k to the 4th as k squared squared minus 6 squared. So exactly, we'll have k squared plus 6 and k squared minus 6. Now is 6 a perfect square? No, there's not a number times itself that gives us 6. The only number that we would actually have is the square root of 6, because the square root of 6 times the square root of 6 would get us 6, but we don't factor with irrationals. So it's kind of a funny yes, no. Yes, it does, but no, it's not nice. So we only want to factor with natural numbers or integers. Questions on this here? We're going to do one more. Yes. So that would give us x squared plus 9 times x squared minus 9. Now the question is 9 a perfect square? So this time we do actually have a difference of perfect squares. Now the sum of perfect squares does not factor into real terms. So we leave it as x squared plus 9. But how would x squared minus 9 factor? And x, yeah. So x squared plus 9 times x plus 3 times x minus 3. So we could have it in either order, because the x minus 3 and x plus 3, it doesn't matter which one we put first, as long as they're both there. Yes. And this here would be the final answer. Now, I'm going to go on and show this. You don't have to write this down kind of as a reasoning why this works the way it does. Because if we were solving this, these factors really give us the solutions. Is x minus 3, what value of x would make it be 0? Is positive 3. X plus 3 would be negative 3. So positive and negative 3. So if we took x squared minus 9 equals 0 and solve for this here, well, we would add 9 first. Telling us x squared is equal to 9. Square root both sides. Whenever we square root both sides, we have to add the plus or minus, so we get plus or minus 3. Those are real numbers, yes? Now the other part was x squared plus 9 is equal to 0. Well, the first step is to minus 9 from both sides, telling us x squared is equal to negative 9. Square root both sides, we get x is equal to plus or minus. We would have 3 from 9, but the negative comes out as 3i. Is 3i a real number? No. So we don't have real factors. Because when we talk about factoring, we're really talking about the real factors. X squared plus 9 will technically factor, but it factors to x plus 3i and x minus 3i. But in order to get the factors, we really have to solve for it and then work backwards. So we don't mess with it. We only talk about the real factors of it. So that would be it. Questions on this here? There are two other types of factoring that are in this note sheet that we will look at. One of them is the sum and difference of perfect cubes, and the last type is factoring by grouping. And most likely we're going to leave factoring by grouping to tomorrow. We'll finish it up and then you'll have the rest of the time to work on the homework. So factoring sum and difference of perfect cubes. This is kind of nice that it works out this way every single time. As long as we have two perfect cubes being added or subtracted, it'll work in this way here. The signs have a specific pattern. It's going to be the same, opposite, always end on a positive note. So when we have plus, it's going to be plus, minus, plus. If it starts out at subtraction, it's going to be subtraction, plus, plus. Same, opposite, always end on a positive note. Now our first term, whenever we find out what it is, so here a, in the small one we'll have a, in the bigger one we have a squared, a to the first, and then a to the 0. It decreases in power. 2, 1, 0. Our second term b, in the first set of parentheses, it's just to the first power. In the other parentheses, it starts off at 0, goes to 1, and then goes to 2. So in the bigger set, the second term is increasing, and the first term is decreasing. And it works with positive and negative. both cases, addition, difference, and sum. So when we look at our first one here, x cubed plus 125, there is no greatest common factor. So we can start off by taking the cubed root of the first and second terms. Now we do this for two reasons. One, to find out what the value of a and b is, or the first and second term is, that we're going to be using, as well as determining if these are two perfect cubes. The easier one out of these two is the cubed root of x cubed. And it is x. Because whenever the index and the exponent are the same, they simplify out. And we'll get more into why that works, especially when we start talking about roots in our chapter over radicals. Now the cubed root of 125 is 5. So we can come into the calculator, say 3 second radical, 125, then it is 5. So we use second and the little caret key button to get our nth root. If it looks like a normal 3 out front, it's not actually taking the cubed root, it's taking the square root and then multiplying it by 3. We don't want that. So the cubed root of 125 is 5. Now we can set it up. So we have a parentheses with 3 spaces and then a parenthesis with 5. Now we need our signs. The signs are going to be the same. Opposite always end on a positive note. So our starting sign is plus. So for it to be the same, we're going to have plus. Opposite would be minus. And on a positive note is going to be plus. So we have plus, minus, plus. Now we can start plugging in the first term. And our first term that we're going to be dealing with is x. So in our first spot, we're going to have x. In the bigger parentheses, first spot we'll have x squared, x to the first, and the last one will technically be x to the 0. And anything to the 0 power is 1. Now our second term is 5. So inside our first set of parentheses, we'll have 5 to the first. We don't put anything with the x squared because technically it is 5 to the 0, which is multiplying by 1. Doesn't change anything. And the middle one will have 5 to the first. And the last one will have 5 squared. And when we simplify this, we'll have x plus 5 times. Here we'll have x squared minus 5 times x, or x times 5 is 5x, plus 5 squared is 25. And that's it. Yep. And that's it. So these aren't too bad once you get the pattern down or understand how the pattern works. Questions on these here? Let's look at this next one here. And again, I like to start off by taking the cubed root of the two terms. That way we can kind of see what they are, what we're dealing with, and if it is the sum or difference of perfect cubes. Well, the cubed root of x to the third is x. Cubed root of 64, 4. Minus, plus, plus. Since we started off with the difference, so the same would be minus, opposite of that would be plus, and we'll end with a plus. And on any of these here, we will not have a sum or difference of perfect cubes that will have 3 pluses or 3 minuses in it. It just doesn't work out that way for our signs that we plug in. Also, when y'all take the ACT, they do throw some factoring in there for some of the questions, and if they throw a sum or difference of perfect cubes in, this right here is one way to eliminate answers. Since it's a minus for 2 cubes, it has to be minus plus plus. Any of them that have factors that don't have this setup, we can mark out they're not going to be correct. So it's one way to easily eliminate answers. Then we can go on to our first term. Here we're going to have x. In our first spot we're going to have x squared and then x. Our second term is 4. So we know the first one's going to have to be x minus 4. Any of the answer choices that they give you for that problem that don't have x minus 4 as one of the factors are wrong, you can mark them off. Inside the other one, there's not a 4 with the x squared, but the middle one has 4 to the first, and the last one has 4 squared. On some of these on the ACT that come up, one of the answer choices is most likely going to have plus 64 or minus 64. I don't know why they like putting 64 in there. They just do sometimes. But we can eliminate that one. But to finish simplifying, we'll have x minus 4 times, well, x squared is going to be x squared, plus x times 4 is 4x plus 16. Any questions on this here? We're going to do 2 more, this one and the next one. I want to look at this one here because out of the ones we've done so far, it's the first one that actually has a number in front of a number in front of our variable. So we'll look at taking the cubed root of 27a cubed and the cubed root of 64. Well, one of these we already know already. Cubed root of 64 is 4, because that's shown up a few times already. Now, unfortunately, we can't type in the cubed root of 27a cubed. We can't type the whole thing in because the calculators need a value for a. Any variable, it needs a value for it. But we know the cubed root of a to the third is a. In the calculator, I'll pull it up, we can type in the cubed root of 27, which is 3. It's kind of cool that worked out that way, 543. So the cubed root of 27a to the third is 3a. And we'll have our same setup. Now our signs are going to be the same. Opposite always end on a positive note. So since we started with plus, the same would be plus. Opposite would be minus, plus. Our first term is 3a. In the first spot here, we'll have 3a squared. Then we'll have 3a to the first. And our last one is 3a to the 0, or just 1. We don't have to put it in. Our second term is 4. So we'll have 4 here. Nothing with 3a. 4, and then 4 squared. And when we simplify this here, we'll have 3a plus 4 times 3a squared. Well, 3a squared is going to be 9a squared minus 3a times 4 is 12a plus 4 squared, which is 16. Yeah, that 3 snuck in there, didn't it? I always find that frustrating. I'll get completely finished with the problem and realize I left a number off at the beginning. Did the whole thing right, just left one number. Questions on this so far? Are you ready for the last one? This one here. So cubed root of 192. Cubed root 192 does not have a cubed root. 5.7689982821. So let's look for greatest common factor. Is there a number that will go into 192 and 81? 3, 9 maybe. We just need to see about 192. So 192 divided by 9, almost. It's just a little too big. But 3 does work. Because it is very tempting to say 9, because 81 is divisible by 9. And that would make things a lot nicer, but 3 is the one we want. 192 divided by 3 is going to be 64, x to the third, minus 81 divided by 3 is 27. Now we could go on and still write out the cubed root of 64 x to the third, but as we've had at least 3 or 4 times by now, the cubed root of 64 is 4, and then we have x. Now the cubed root of 27y to the third, 3y, because we had 27 already and it was 3. Now this one here is the first one we've had that does have variables in both terms. First one we've had that has variables in both. Now our signs are still going to work the same since we start off with minus, so the same would be minus, opposite would be plus, plus, and on a positive note. Now our first term is 4x. Here we're going to have 4x squared, 4x to the first, and then the last one is 4x to the 0. We don't have to include it. Our second term is 3y. We don't put one first, but the middle would be 3y. And lastly, we'll have 3y squared. And if we simplify this, we get 3 times 4x minus 3y times 4x squared. Well, 4 squared is 16x squared plus 4x times 3y. 4 times 3 is 12. And we have xy. Lastly, we have plus 3y squared. Well, 3 squared is 9. And y squared is, well, y squared. And that's it. Questions on this here? Questions on anything we've done so far? Now, these special cases, I find it interesting, and this is also kind of why I find math as interesting as I do, is that stuff like this sum and difference of perfect cubes works. No matter what the two terms are, as long as they're perfect cubes, this works, and we get this here, we get this breakdown. Does that kind of make sense? Even as we saw with the difference of perfect squares, even though it wasn't x squared, or term squared, it was to the fourth, it still worked. And then we could simplify further. I'm just going to throw this up here. It's not in your note sheet. But just kind of reiterating this point. We could talk about, powers of powers, yeah. We could say x to the 6 minus 1. There's different ways we can look at it. Because I could say this is x cubed. Let's just, powers of powers multiply. So x to the third to the second power is really x to the sixth. Difference of perfect squares. So x cubed minus 1 times x cubed plus 1. And then we can treat it as difference of perfect cubes. So it would be x minus 1 times x squared plus x plus 1. And this one here would be x plus 1 times x squared minus x plus 1. So essentially I could use both of them to get there, but it still works no matter how we set it up. They still work. We won't get to something this complex. Most college algebras don't get to something this complex. Again, as I said before we started this, over and above. But we're going to